All right, everybody, welcome back. This is going to be the third video of Chapter 1, and this one is going to this video is going to cover everything about drawing structures. One thing that we've been doing so far is that we've been drawing all the structures very painstakingly detailed in terms of drawing every single little bond, drawing every single little H or other atom. This gets really tedious, as you guys probably are understanding by now, right? So wouldn't it be great if there were shorter ways of doing this? As it so happens, there are. There's a couple of different systems. One of them is one that you've probably seen before. It's called condensed structure. And the other one you may not have seen is called skeletal structure. They both have their advantages. I think skeletal structure is way, way, way better, but I want to show you both of them. All right, and I'm going to start off with condensed structure. All right. So the first thing to realize about these systems is that they're going to have some rules. All right. There's going to be some guidelines to how we go about converting these expanded Lewis structures into little condensed structures. All right. So here we go. Here's condensed. All right. Number one, you do draw all the atoms. But generally, running out of room, not the bonds. And I put generally because one thing that you're going to see that's kind of aggravating about condensed structure sometimes is that it can be a little bit ambiguous, and there are some different interpretations. And I'll actually show you an example of this as well. Sometimes multiple bonds are actually drawn in. Multiple bonds being double or triple bonds. Sometimes they're not. And again, like I said, there's a few different little nooks and crannies and tweaks and stuff that people use in condensed structures. That's going to be one of them. The atoms are usually, cannot spell usually, there we go, are usually drawn next to the atoms they're bonded to. Alright, and I say usually because it's going to be impossible to have them all like that, and you'll see why. It's something that really bears itself, shows itself better in examples than it does than just straight up statements. All right. Number three, we make use of parentheses quite often, and we do it for a couple of different reasons. Parentheses are used around similar groups on the same atom or similar groups in a series. Again, this will make more sense once we go over the examples. So make sure to write all these down and then just sort of maybe take a screenshot or something, or have your paper ready while we're doing the actual examples, and you can sort of see how they apply. And then lastly, we don't bother to draw the lone electron pairs. You have to be able to recognize that even though they're not drawn in, they should be there. All right, and that really is rooted in understanding those rules, those tables that I gave you in the previous videos. So no unshared pairs. All right, well, like I said, the best way to learn this is to go through actual examples. So let's start doing some examples, and I have several of them here. actually, I'm going to switch it up a little bit. I just thought of a more efficient way to do this. I'm going to go ahead and present the rules for skeletal structure as well. And then for each example, I can draw both a skeletal and a condensed structure. Yay me. All right. Skeletal is the form that I use most often. It's really, really quick and efficient and easy to use, and I think easier to understand than condensed structures. Basically, in skeletal structures, instead of having a bunch of atoms, you mostly have these little zigzag lines. All right? So the first rule is you don't draw carbons or any H's that are attached to carbons. You do draw the lines. The lines represent bonds, right? So the lines are going to represent electrons, all right? So let me show you a quick example of something like this, right? This might be an entire skeletal structure, right? In the zigzag drawing, every corner is a carbon. Right? So you could look at this one I just drew, and I'll circle them. There's a corner, there's a corner, there's a corner. So each one of those carbons has, each one of those corners represents one carbon, so this structure has 3 of them, all bonded in a row. Okay? Like I said, we don't draw the H's that are attached either, right? What we do is we assume that you have enough H's on the carbons for tetravalency. And if you're not familiar with that term, basically that just means that you have enough H's to give carbon a total of 4 bonds and give it 8 electrons in this octet. Right? So if you look at the first one right here, right, that carbon, you can see 1 bond to one other carbon. So that means we're missing 3 bonds, so this carbon must have 3 H's attached to it. Same thing for this guy over here, right? We can see 1 bond attached to this corner, so the rest of it must be filled out with 3 H's. This one over here, you can see 2 bonds already drawn, one of them to each carbon on each side. That means this one must have 2 H's. Okay. Lastly, we do draw all heteroatoms and attached H's. Simply put, a heteroatom is any atom that is not carbon or hydrogen. So nitrogen's a heteroatom, oxygen's a heteroatom, halogens are heteroatoms, basically anything that's not carbon or hydrogen. All right. Now, let's take a look at some more in-depth examples. All right. So, let's start off with this guy. We're going to use a 5-carbon unit. This is a molecule called pentane. And I'm drawing out the expanded structure first. And this is very, very tedious with the stylus. So I'll be really glad when we don't do these too much anymore. That will be soon. Alright, so here is the expanded structure of pentane. Okay, so first I'm going to talk about condensed structure. And like I said, condensed structure is a little bit aggravating sometimes because there are some ambiguities to it. There's oftentimes more than one correct way to draw a condensed structure. And in fact, in this one, there's a couple of different ways that you can draw it. Generally speaking, when you do a condensed structure, you kind of go left to right. And you have to try to make sure, again, to respect the rules of tetravalency for carbon. All right? So, I'm going to start on the left here. We have a CH3 group, right? A carbon with 3 H's. I'm just going to summarize it like that. Bonded to this, we have a CH2 group, so I can just write that sort of collectively. And next is bonded another CH2 and another CH2 and a CH3. And boom, there is a condensed structure. You see, we've taken out all the bonds to the H's to make it a little bit more efficient. Some people would prefer to draw this like this. Instead of putting CH3 at the end, they like to put H3C to make it a little bit more apparent that the hydrogen is not, this hydrogen over here is not bonded to two carbons. Again, that's just sort of a matter of preference. You can do it either way. But if we drew one like that, that would be fine too. Also, though, like I said, we can use parentheses to our advantage. One of the things we said we can do with parentheses is use them on similar groups in a series. And we can see that we have 3 CH2 groups all in a row here, right? So one thing that we can do is I'll just do it this way. One thing we can do is just say we have the initial CH3 group, and then in the chain you have 3 CH2 groups in a row. If you write it like this, this implies that you have CH2, CH2, CH2. All right, and then boom, we have our CH3 on the end. Any of these would be, perfectly acceptable condensed structures. All right. Now let me show you the skeletal structure. Skeletal structure, like I said, is a lot quicker, cleaner, I think easier, and much more direct. There's less ambiguity as well. If we wanted to do this, we would just simply write that. Boom, done. Isn't that fast and easy and quick? So much better than drawing out all the little details. But it makes sense, right? We said every corner is a carbon. This carbon chain should have 5 carbons, and 1, 2, 3, 4, 5, right? The end carbon should have 3 H's, all right? 1 bond is already drawn on this carbon, so we have to have 3 H's to fill out tetravalencies. This is going to have 2 H's because it's already got 2 bonds shown, right? And we see we have 2 H's here, 2 H's here. There we go. CH2, CH2, CH3, right? Very nice, quick, and efficient way of representing pentane. All right, let's try another one. Let's try this one. Sorry, I'm running out of room here, so I'm kind of squishing this one up top. Come on, draw the... Dang it. Limitations of technology, folks. I have to start down lower. Don't do it again. Come on. Oh my god, this sucks. Now is when you can laugh at me because of my trials and tribulations with technology. Oh, fine, I'll just do it down here. Okay, so there's another one. It's a really ugly H. Let me fix that. There we go. All right, so there's another one. All right, so first I'm going to draw it in skeletal form. Again, there's a couple of different ways you could draw this. You could draw it like this. We kind of have a centralized carbon here, right, that a bunch of other stuff is attached to. Now, so we could say, something like this, HC. All right, and then we have 3 different CH3 groups that are bonded to this. So we said there was one other instance in which we used parentheses, and that's if you have similar groups that are attached to the same atom. So you could just simply say parentheses CH3, 3, and that indicates that you have a centralized carbon right here that's got 3 methyl groups, or excuse me, 3 CH3 groups attached to it as well as an H. You could, write it like this too, if you wanted to. That would be perfectly fine. The H in front, or on the left or the right, is really more of a stylistic preference there. You could also write it like this, where you put the methyls on the left and the CH on the right. Any of those would be perfectly fine. They all represent the same thing. All right. If we want to do this in skeletal form, we can do it like this. Boom, that's it. Isn't that so much better? Again, we have a centralized carbon, right here. And that centralized carbon is going to have 3 CH3 groups on it, here, here, and here. And remember, not shown, we're also going to have an H on that central carbon. Remember, we don't draw them. So you see that this central carbon here has 3 bonds. If you see it has 3 bonds already drawn, then you can assume that it has 1 H. After you practice this for a while, you will almost guarantee, I will almost guarantee, fall in love with skeletal form, and you'll never want to go back to the other ones. It's so much easier. Alright, let's try another one. Oh my gosh, this is a big one. I'm going to need a lot of space here. So in case you're wondering my process for this, as much as I'd like to think that just genius just rolls off the top of my head, I am actually doing this from a script, so I write up all the notes ahead of time, and then I do the iPad recordings. And I'm wondering to myself, why did I make an example this large? So much easier to do on paper than it is on the iPad. But that's okay. We're almost done. Phew, okay. That's a lot of stuff to draw out. All right, but you can see, again, we have multiple carbons there. Let's see if we can find ways to reduce that. Okay. All right, so if I look over here, I see I've got a carbon, and it's got 2 CH3 groups, so I'm just going to go ahead and represent that. HC. Actually, whoops. I'm going to do it like this. CH3, 2, attached to CH, right? That CH is then attached to another another carbon right over here, right? We have CH2, and then another CH2, and then we have a CH that again has 2 different CH3 groups attached to it, so it looks like that. Right? Alternatively, you could have also done this. Where you drew these 2 in a series and put them in parentheses. That's the thing people get hung up sometimes, is they kind of forget that the parentheses can be used for 2 different things. You have to be able to, if you're interpreting a condensed structure, you got to be able to recognize which way is being used at a given time. And you just use common sense rules of tetravalency, right? The charts that we learned previously to kind of figure it out. Because usually it'll make complete sense one way and no sense the other way. Right? But these are a couple of condensed structures that you could use for this expanded Lewis structure. All right. Now let's do a skeletal structure. Well, I think the easiest thing to do is, first of all, just try to identify a continuous chain, right? if I look, crud, my eraser was on. Oh well, it's alright. If I look here, I can identify a continuous chain of 6 carbons, so I'm going to start there. Alright, so this 6 carbon zigzag here, right, and we can see 6 carbons, 1, 2, 3, 4, 5, 6. That represents the 6 carbons of that chain. We also have a CH3 group hanging off of this carbon, so we're going to have a CH3 group there, and we're going to have a CH3 group hanging off that carbon. So, here, let me draw it without the circles because that's bothering me. So this is what the skeletal structure for this Lewis structure would look like. Okay? Any questions? No? No? Not hearing any? Wow, you guys must really know what you're doing. Ha 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 ha. Alright, more examples. Here, let's do something a little bit different. Let's introduce a multiple bond. We're going to do something with a double bond. Alright, let's say we had this. Okay, so there's a couple of different ways you could go about doing a condensed structure here, right? First of all, we could just do it like we normally would do, right? Looks like we have a CH3 on the end. Then we have a CH group, and followed by another CH group, and then a CH3. So, boom. That would be a good condensed structure. We could also, put those 2 CHs in the middle, in parentheses, just to shorten it up a little bit. That would be perfectly good. All right. There's one other way that you will see this done sometimes, and this honestly is the kind of a thing that bothers me about condensed structure because it's so ambiguous, but being realistic, you do see it represented like this from time to time. There are some times where people will draw, when I say people, that means even like textbooks and official sources, they will draw the double bonds. All right? So, for instance, this would also be an acceptable condensed structure. In this case, we're going to show the double bond between those 2 middle carbons. So any one of those 3 would be perfectly fine. Okay, so be sure to keep that in mind. You might see a double bond or triple bond drawn in, you might not. Just depends on the source. Skeletal structure, super easy. We have a 4-carbon chain, right? And the middle 2 carbons are double bonded, so we just simply draw another line. Okay? This carbon over here has 3 bonds on it, right? 1 from the single bond, 2 from the double bond. It only has 1 spot left, so you can tell it's only got 1 hydrogen. Same thing for this one. All right, let's do a couple of examples with heteroatoms. We haven't seen heteroatoms yet. All right, let's try this one. This is ethanol. All right, it belongs in the family of alcohols. And like any other alcohol, it has got an OH group. All right, so be sure to draw everything. This is Lewis structure, so I have to draw in the electrons and all the bonds. All right, so if we're doing this in condensed form, you can just simply say you have CH3, and then you have CH2, and it's an OH. That means you can just sort of collapse the O-H all into just an OH group. Yeah, so if you see OH in a condensed structure, that means you have an O bonded to H. If we wanted to show this in skeletal form, very simple. We have 2 carbons, all right? But instead of leaving this third corner there, we're going to put OH on it. So as a result, we have corners, empty corners here and here, right? That represents our 2 carbons. And this carbon is bonded to the oxygen using those electrons. And that represents this bond right over here. All right? Just like we do in a condensed formula, we are not required to draw the unshared pairs. You do have to realize they're there. If you draw them, I'm not going to penalize you, but just know that I'm not going to draw them. All right. So that is ethanol. Let's try one like this. Let's see. Oh, let's put some halogens in there. Let's liven it up a little bit. Alright, so we're going to have that. We got an H down there. CH2. CH2. Put an O in here. CH3. 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 Huh. Shoulder's getting tired. A lot of work writing these structures. Alright. Alright, so, again, let's do a condensed structure for this one. I see this end carbon has 2 Cl's on it, so I'm just going to put Cl, parentheses, 2 of them. We have a CH. I'm not going to go through and write every iteration of the condensed formula here. I'm just going to go ahead and do a quick correct one. You definitely, I think at this point, can kind of get them, figured out on your own. We have another CH. We have another CH. We have an oxygen. And then we have a C. This 3 CH3s. Whoops. What the heck am I doing? Boom. Okay. Now, if we wanted to represent this in skeletal structure, all right, what I like to do first is kind of try to get, most of the carbons taken care of. I know I'm going to have a 3-carbon chain here, so I'm going to go ahead and draw those. That's 3 carbons. I know this carbon at the end is going to be bonded with this oxygen, so I'm going to draw another bond, put an oxygen on it. And on the other side, that oxygen is bonded to a carbon, and that carbon has 3 CH3 groups on it, represented there, there, and there. And now I can go back at the beginning. I know that first carbon has to have 2 Cl's, and viola, you have your skeletal structure. Nice and clean. All right. All right, at this point it's worth mentioning that there are certain groups that are a little bit harder to identify in condensed structure. So I want to just give you a shortcut on what these mean. This is also in your book, by the way. Your book probably has much better tables and artistry than I do, but I want to discuss this with you briefly. All right. Sometimes in condensed structure, you will see this group represented, CHO. Important to note, that is not OH. HO is very different from OH. All right? This means that the H is directly attached to the carbon, not to the oxygen. Right? This commonly represents something called an aldehyde group, and that is a carbon double bonded to oxygen and single bonded to H. Okay? You also will sometimes see CO represented. All right? That's a carbonyl group. And that is equivalent to C double bonded to O. And sometimes you'll also see CO2. That means you have a carbon double bonded to O and also single bonded to another carbon. Okay? Those look a little funny sometimes, and that can be a little bit tricky for beginning students to get the hang of. So I wanted you to be aware of. It'll probably make your life easier if you can just put these 3 to memory. All right. Let me show you a couple of examples. All right. Let's try this one. Okay. So this is going to have a CO2 group in it, as you can see right over here. All right. So what we can do is we can say we have Cl attached to a CH group attached to a CH2. All right. Then we will represent this group over here with CO2. And lastly, one of the O's is going to have the H. You can just simply put that on the very end. Sometimes, and again, I apologize for this, but it is something you run into. Sometimes you will see CO2s split up. And so sometimes you might see it written like this. That means the exact same thing as the previous condensed structure. All right. If you wanted to draw the skeletal, it's much simpler. There's your 3 carbons. Carbon over here on the end we know has a double bond to oxygen, and it has an OH group hanging off of it. Come on, there we go. And then the carbon on the left has a Cl. All right, I'm going to do one more example, then I'm going to be done. Got to finish soon because my iPad's losing charge pretty quickly. But this will be the last thing. All right, let's try this one. All right, this is a type of molecule called a ketone. Okay. So this one's pretty straightforward, CH3. We have a C double bond O, right? So we're just going to simply represent that as a CO. CH2, CH3. All right. Skeletal structure, we have 4 carbons in a row, so let's draw a zigzag. That gives us 4 corners. We know that second carbon from the left is going to have a double bond O, so we draw it like that. Boom. All right. So now that we know how to do this, I am going to take mercy on my elbow and shoulder and not do complete Lewis structures very often, but I'll mostly stick to skeletal structures with a little bit of condensed structure here and there. So the sooner that you can sort of learn and get the hang of this, this will make your life a lot easier as well. There's lots of good practice problems in the book and in Sapling, and like I said, once you do this for a little bit, this will become second nature to you, especially the skeletal structure, and I think you'll appreciate not having to draw every single little thing as well. All right, until next time, I will talk to you later. Bye-bye.